Well, welcome to Stars, Cells, and God. This is a podcast where we talk about the latest scientific discoveries that give us even stronger evidence for the Christian faith and the inerrancy of the Bible. And your gateway to everything social media at Reasons to Believe is RTB_official. And that will take you to our Facebook, Twitter page, Instagram, everything else you can think of in social media. And please, if you're not already a subscriber, subscribe to the Reasons to Believe YouTube channel. Literally thousands of video clips are up there. And if you're a subscriber, and by the way, subscribing is free. But if you are a subscriber, you'll be notified of the videos as they're being posted there. So Fuzz, you're going to launch off today with something about skin, I think.
Yeah, so to set the stage for my discovery, I want to just have a little bit of fun for a few minutes, if you indulge me, Hugh.
Not a problem.
But I don't know if you if you and Kathy subscribe to the Disney channel, the Disney Plus channel.
No, we don't.
Yeah.
Our kids have left the home. So.
Yeah, well, I actually subscribe to the channel, and part of my motivation is, in fact, my total motivation is that's where the movies from the Marvel Cinematic Universe are housed. And then also Disney Plus is creating original programming where they are producing these series featuring some of the Marvel characters.
And I'm anticipating that some of them got super skin. Is that what you're telling me?
No, none of them have super skin. Well, actually, there are probably superheroes with super skin, but none of them are I'm not going to refer to any of them. But there is a series on Disney Plus. It's an animated series, and it's called What If? And I actually hesitated to even watch the series because it was animated, but I eventually broke down and watched the first episode and found it to actually be really good. But it's an interesting premise. It features a character called the Watcher, who is a member of this alien civilization. He with superpowers and super intelligence. And the Watcher's primary role is to observe events that are happening in the universe, and they take an oath not to intervene or interfere.
Kind of like we astronomers. We don't get to interfere either.
Yeah, you just observe. Yeah. So kind of like us astronomers, I guess you might say. But the What If series is about the multiverse and about alternate timelines, where the premise is, what if a certain event happened differently in Marvel history? What would be the ramifications? Okay. So what if Peggy Carter became the first Avenger instead of Steve Rogers? Or, what if Ultron defeated the Avengers? Things like that. And so it's a lot of fun. But what is the point that's being driven home in that series is that sometimes a single event happening differently in history can lead to a radically different future. And that concept, believe it or not, is actually part of evolutionary biology. Right? That there are some biologists who view evolutionary history as being contingent.
Stephen Jay Gould would be a prime example.
Yes, he was the person who probably articulated the idea the best and really popularized the idea. And the notion here is that evolutionary history is comprised of a sequence of chance events, and that if one of those events happened differently, evolution would go in a radically different direction.
And we probably wouldn't be doing this podcast.
That's right. So his metaphor was that if you rewound the tape of life and replayed it, that the outcome would be different every time. That's the way he conceived of the idea of historical contingency. And again, when you think about the nature of the evolutionary process, again, it is an unguided, undirected process predicated on a sequence of chance events where evolution is using existing designs and modifying them and cobbling them together to create new designs. And you would not expect the evolutionary process to independently arrive at identical outcomes because of the historically contingent nature of the process, that one of the predictions would be that it's simply not repeatable. Mm-hmm. And yet what we have learned is that when we look at the record of nature, is that we see what appears to be evolutionary events independently hitting upon identical outcomes. Evolutionary biologists refer to this phenomena as convergence, where evolutionary processes converge on identical outcomes or
Buzz,
nearly
you've been
identical.
keeping kind of a running list of this. How big is the list now of these examples of identical convergent outcomes?
Well, I haven't actually kept a formal list. From time to time I'll talk about this.
But I know it's in the hundreds.
Yeah, well, in the book The Cell's Design, I catalog just for fun 100 examples of convergence that happens at the at the biochemical level. But there are people like Simon Conway Morris in his book Life's Solution, which was published, I think, in 2004 now, who catalogs a large number of examples of convergence. There's another book written by an evolutionary biologist by the name of George McGee, and the book is called Convergent Evolution, who also catalogs examples. But the point here is that convergence is widespread. It's characteristic of the
So we're not just talking one or two examples.
right, and it's at the anatomical level, the physiological level, the biochemical level. We see it at the genetic level even, and it's one thing if convergence occurred occasionally as an odd phenomena, but the fact that it is characteristic of the living realm really suggests that the evolutionary process is not historically contingent. And of course, this is problematic because when you look at the nature of the mechanism, it must be historically contingent. So you have really, in a sense,
That's from a naturalistic perspective. It must be.
Yeah. You really have in a sense, what constitutes a failed prediction, or features in nature that are really not what you would expect. And what I want to talk about today is another example that was published recently in a journal called Current Biology by a really large team of collaborators who identify another example of convergence. And this is a surprising example, by the way. It involves the skin of whales and hippos. Now, the reason why people are interested in the skin structure of whales and hippos, at least in an evolutionary context, is there's a lot of interest in evolution happening at the water's edge. So when you look at the history of life on Earth, one of the key events was the migration of animals from the water, the oceans, onto the land. And so this would have happened somewhere in the 380 to 400 million year window of time, where presumably, in evolutionary terms, a lobed fin fish underwent a series of transitions that are dubbed fishopods that resulted in the emergence of the very first land-based animal, which would have been an amphibian, acanthostega or ichthyostega. Then also, when you look at the history of life on Earth, there's another series of events that happen at the water's edge, presumably, and this is where in combination with the mammalian radiation, where we now have mammals going from the land back into the ocean, where you have the evolution, presumably, of terrestrial animals that become aquatic animals. And they can be semi-aquatic, like a hippopotamus, or they can be fully aquatic, like the cetaceans, for example, whales and dolphins. Mm-hmm. So the big question is, how does this transition happen? Now, initially, people, based on morphological features, argued that that whales were, today people believe that whales, from using DNA data, are actually part of a group known as the arctodactyls, which would be the even-toed herbivores. And whales actually group with that particular cluster. But based on morphological data, initially people actually didn't see cetaceans in that group, but saw them as a separate group. Likewise, with the hippopotamuses, they were actually, based on morphology, clustered with pigs. But based on genetic data, genetic comparisons, people actually cluster them with the cetaceans, where they are considered to be the closest group in evolutionary terms, the sister group to cetaceans. And so when it comes to the transition from again, a terrestrial animal to an aquatic animal, there's a number of anatomical and physiological changes that take place. Many of them involve actually the skin structure. There's a very different in characteristic structure of the skin that both whales and hippos have that reflect that transition from an aquatic lifestyle, from a terrestrial lifestyle to an aquatic lifestyle. And so this particular paper is looking at, again, what does that transition involve? And this is a diagram showing a very simplistic evolutionary tree. And on the top diagram, you see essentially cetaceans and the hippos as being, again, these sister groups. And presumably the shared aquatic features with respect to the skin arose in the hypothetical ancestor that gave rise to those two groups. That would be the most simple, parsimonious explanation for how these two organisms would have identical features. However, when the genetic basis for those aquatic characteristics was analyzed, what was discovered is that there were 10 genes that essentially became disabled in both the whale and the hippo lineages, identical genes producing these aquatic features. But what they discovered is that the time frame in which those genes became disabled was radically different. And on that basis, they conclude that actually the way to explain these features is as if you have two separate independent evolutionary events involving the same 10 genes that essentially become disabled. And so from an evolutionary perspective, it looks as if the skin structure of whales and hippos, again, would have evolved independently, but would have produced identical structures.
And when you say identical structures, how are they identical?
Well, in terms of the loss of hair follicles, the loss of sebaceous glands, there are these histological features that are identical that, again, reflect living in an aquatic setting versus a terrestrial setting in terms of insulation and things like that, those kinds of features. So there's a fairly extensive list of those features. I may have actually written it down someplace. So it would be the loss of the hair follicles, loss of sebaceous glands, and then so those would be the two primary changes that you see in skin.
I imagine the skin of the hippos is a little thinner than it is, say, for an elephant or a rhinoceros.
I don't know if it's thinner or not, but you have probably a lot more insulation connected with the skin, just in terms of helping to retain heat.
Right.
Living in an aquatic environment. So the point here is that, it looks as if from an evolutionary perspective, it's not just simply that the skin structures are identical, it's that the genes that are involved in those skin structures have actually, it's the same 10 genes that have been lost. And you might think, well, losing genes isn't that big of a deal, but to lose genes in such a way that that gene loss with 10 different genes is coordinated and orchestrated in such a way to produce viable, functional, anatomical and physiological features that promote survivability in an aquatic environment is just as remarkable as acquiring 10 new genes to give a new biological feature. So just because it's involving gene loss doesn't necessarily mean it's somehow easier to attain that outcome. There still has to be this high degree of coordination, of the effects of that gene loss in order to produce, again, these coherent changes that produce functional biological structure. So it's a rather remarkable example of convergence in that sense, because again, it involves identical genetic changes. So this again is not what you would expect from an evolutionary perspective. And in and of itself, this is one example of convergence isn't necessarily enough to say maybe evolution isn't the best explanation for life's history.
Yeah, one could be a coincidence, but not 500.
Right. But so this is really, added to that mounting list. And what's interesting to me is that we continue to discover more and more and more examples of convergence. So the trend line is growing, not lessening. And so to me, the idea of convergence, not only is it problematic for the evolutionary paradigm, but I would argue that it's exactly what we would expect if indeed life's history has been orchestrated by a creator. Where instead of thinking about convergence in evolutionary terms, we might want to use a different term that people like Sir Richard Owen use, which are called analogies, where he argued that there are shared biological features in organisms. Some of those features are shared in organisms that would naturally group together. Those were called homologies. Other features are shared in groups of organisms that don't cluster together, that don't naturally group, and he called those analogies. And he saw both homologies and analogies as reflecting the work of a creator, where analogies would involve the creator utilizing the same designs in different groups of organisms that are being confronted with the same kind of problem. And so when you think about the aquatic structure of the skin of whales and hippos, if you think of them as analogies, then you could think of these as being features that a creator intentionally designed so these organisms could thrive in an aquatic environment.
Well, Fuzz, I've been to Africa a few times. I've gotten fairly close to these hippos, and I was with a biologist and one of them, and he was talking about how evolutionists like to cluster hippos with the cetaceans and basically classify them both as aquatic animals. But what he's explaining to me is it's really a mistake to classify hippos as aquatic. Namely, they do all their feeding at night on the land. They go into the water during the daytime. He says there's a good reason. If you look at the hippo's body, you've got this very large, almost spherical structure for its body, which means given its size, it's in danger of overheating. And so what the hippos do is they go into the water when it's really hot out, submerge themselves to prevent their bodies from overcooling. But he says they don't eat in the water. They're basically resting and sleeping. And at night is when they do all their activity, when the sun's not out. So his comment was they're really terrestrial animals that are cooling off in the water during the daytime. But as you point out, their skin is designed to handle that.
So the hippos are, spending significant time, in the water. And in fact, I think they are referred to technically as semi-aquatic to your friend who is a biologist point. There's one other thing I want to talk a little bit about with regard to this idea of convergence. And this has to do with an idea in evolutionary biology called structuralism. And to me, this is a fascinating idea that I was first exposed to in 2004 when I read Simon Conway Morris's book, Life Solution. Simon Conway Morris is actually largely responsible for the modern day presentation of this idea.
We interviewed him on a Creation Update episode a couple of decades ago.
Yes, we did. He's a fascinating individual. He's a theist, a Christian theist. And anyway, Simon Conway Morris argued that, in a sense, like we're arguing, that that if evolution is historically contingent, you wouldn't expect to see widespread convergence, but we do see that, which means to Simon Conway Morris, evolution can't be historically contingent. And this to me is problematic because when you look at the nature of the evolutionary mechanism, you would conclude naturally that it is indeed historically contingent. And so the way Simon Conway Morris, who actually would consider himself to be an evolutionary biologist, works around that issue is to argue that convergence is telling us something fundamental about the nature of evolution. And he argues that it's telling us that it's not natural selection that is actually determining evolutionary outcomes, but rather there are what you might call laws that are dictating the endpoints of the evolutionary process. So in his book, Life's Solution, he says this, it's now widely thought that the history of life is a little more than a contingent muddle punctuated by disastrous mass extinctions that in spelling doom for one group so open the doors of accidents of history. Yet what we know of evolution suggests the exact reverse. Convergence is ubiquitous, and the constraints of life make the emergence of various biological properties very probable, if not inevitable.
So is he arguing for hidden laws of physics?
I wouldn't say hidden laws of physics. I think he would say that it's the laws of physics that are endemic in the universe itself
Yes.
that actually produce what he would call biological laws that we've not discovered.
So it's the biological laws that are undiscovered.
Right. And that these biological laws essentially are, again, arising out of the laws of physics. They're a manifestation of the laws of physics, but they essentially constrain evolution. And so this is another way that people think of this is that evolution is guided by physical forces which shape the development of the animals' bodies. In other words, that again, it's not natural selection that is producing biological forms. It's essentially the laws of physics that are only saying certain biological forms are possible. Therefore, when evolution takes place, it always goes to the same point, the same endpoint. And another way to think about it, this is Michael Denton's ideas, is he refers to these as the laws of form, or that these are types. That in other words, there are the laws of physics specify particular biological types, and those are the only forms that are actually possible in the universe. And therefore, when life evolves, it always is going to go to these different forms, which is why you see widespread convergence, where the argument is that convergence is evidence that there are these predetermined outcomes. That's, I think, the point that really that they're both Denton and Conway Morris are getting at, is that it's as if things have been predetermined ahead of time by the very laws of nature itself. And what's eerie about it is that if the laws of nature are actually constraining these particular forms, and that these forms actually turn out to be exactly the types of forms that you would need for life to be possible, for life to thrive, for the diversity of life that we see on Earth, it's almost as if there is a mind that has predetermined the outcome. Because you could argue that these laws of nature would constrain, certain biological forms that would be completely useless in any kind of environment. But instead, what we see is that these forms are these highly optimal, well-designed forms. And so Conway Morris actually sees a teleology to the evolutionary process. It's not an unguided, undirected, non-teleological process, but it's a predetermined outcome that is arising from the very nature of the universe itself.
Well, does Conway Morris get explicit about, hey, I can understand, for example, gravity would constrain the different forms of animals. You're not going to get land animals without water support bigger than elephants because of the law of gravity. But it's a rather weak constraint on the morphology of animals. And therefore, does Conway Morris say, hey, the laws of physics by themselves are not going to explain the degree of convergence?
Well, and again, we have to think about the laws of physics in a sense producing like the laws of chemistry, which then in turn are with a combination of chemistry and physics are producing kind of biological laws. So these are laws that arise out of the laws of physics, but they are operating at a different regime of complexity, right? And so, for example, some of this may be topological constraints. So I've seen papers where people are talking about the early stages in embryological development where cells begin to migrate relative to one another to go from kind of a marilla, like a berry-shaped structure,
Sure.
to one that has different cell layers that begins to start to assume forms, that process is actually dictated by topological constraints. So as the cells begin to replicate, there are just these topological effects that force
I would agree
those
we
structures.
observe the topological effects. Trying to explicitly show how they're caused by the laws of physics, I don't see that.
I've seen papers where people are actually showing those types of things where it's, the cell geometry, the nature of the cell-cell interactions and things like that actually, again, create these constraints. And so the point here is that I don't think anybody has discovered, what those biological laws are, but people like Simon Conway Morris would say, hey, there are these tantalizing clues,
Right.
With convergence that seem to suggest that that this whole process of evolutionary history has been rigged from the get-go, right? And that rig job is producing these highly optimal, well-designed structures.
But rigging suggests a mind as opposed to just random physics operating.
Exactly.
And you're a chemist, Fuzz. I can see where in chemistry you can see how the laws of physics impact the chemical outcomes. I mean, it's in textbooks.
Right.
My problem with trying to blame all this biological convergence on the laws of physics, no one's been able to demonstrate the link.
Well, and I think part of the people, and I don't hold to structuralism, by the way.
Yeah.
I think it's an intriguing idea.
Well,
but,
it raises questions, which I think are very interesting.
Yes, and I would agree with that. But to me, I think the point that people like Simon Conway Morris would make is that evolutionary theory for 150, 175 years has been influenced by this idea of natural selection and the notion that evolution is this historically contingent process. And that is actually preventing us from studying biological systems like a physicist would, where you're looking for these laws that actually seem to be determining the way organisms are, right? And so part of the motivation behind structuralism is to suggest that this is a legitimate alternative to kind of a Darwinian view of evolution that actually, very well may explain why we see things like convergence, that's so widespread. But this idea is strongly resisted, by the way, by many evolutionary biologists because they see it as teleological.
Right.
The last thing you want to do in biology is introduce teleology, right? And so people are fundamentally opposed to it, not because there's suggestions that legitimize this as an area of exploration. It's because nobody likes the teleological effect. So the point is that I'm really trying to make with this is that when it comes to convergence, you really are, if you are a strict materialist, you're between a rock and a hard place. Either convergence is pointing to a creator directly intervening in deliberate ways, to produce the same designs over and over again, or a creator has rigged evolution at the very onset so that it only goes to outcomes that the creator has already predetermined, right? So either way, you're left with this idea that there must be a creator that has determined that the history of life looks the way that it is looked.
Especially given that the outcomes are optimized.
Yes, that again is very intriguing, and it's a point that Simon Conway Morris makes again and again, is that these are highly optimal systems that we keep that keep appearing independently, whether it and so the analogy I like to use is that suppose there's a valley, and I find the perfect location in the valley, the lowest point, and I dig a hole there, and then I fit the hole so that this red ball that I have will fit perfectly in that hole. So I can place it there. That would be maybe how you and I would view the creation of life. Or you could maybe create some kind of very elaborate apparatus so that when I roll the ball down that apparatus, no matter where I start that process in the ridge, it's all going to wind up at the same location in the valley, exactly where.
Yeah, if you got a perfectly parabolically shaped valley, it'll work.
Yeah, yeah. But the point is that it works because somebody has rigged
right.
the process in such a way that it's going to wind up exactly where he or she intended it.
Mm-hmm.
So whether you're putting the ball there or the ball is arriving there through a rigged apparatus, either way it's designed.
Right.
It's just what is the mode by which the creator affects that design. So anyway, so to me, this idea of structuralism is I'm not convinced it's correct, but it's an intriguing idea that I think really begins to create kind of bridge points between old Earth creationism and in a position like theistic evolution, right? Where you now are looking at questions about what is the mode of divine action as opposed to whether or not a creator is responsible for life.
Well, once you accept that there is a creator with a powerful mind that's behind it all, then the scientist's job is, how did God actually pull it off?
Yeah.
And that's something that's often ignored in scientific research. Let's actually dig in and see how.
Yeah. Yeah. So anyway, so that's all I have for that.
Well, it's very good, Buzz. I
Yeah.
mean, that's, and you've written a lot on convergence on our website.
Yes.
So if people go to reasons.org, they'll find, I think, well over a dozen articles
Yeah.
that you've written on convergence.
Yeah.
So good.
Yeah. And then as we transition to your discovery, Hugh, we want to take a quick moment to do a quick commercial break and actually let our listeners know of a really exciting opportunity for them. And in, I think, 2018, Ken Samples and I co-authored a book called Humans 2.0, where we look at the question of transhumanism. And this is the idea that we should use technology as a way to motivate. Sorry, we should use technology as a way to modify our biological makeup as human beings, where we would enhance our capabilities beyond our natural biological limits. And this raises all kinds of interesting ethical questions about human enhancements. But there's this idea of transhumanism, which basically argues that these kind of enhancements may provide the way for us to overcome death and to create a practical immortality for human beings. And so I see transhumanism as a direct challenge to the gospel and one of the most...
And to the laws of thermodynamics, right?
Yeah. But it's going to be an idea that's highly influential. If it already is, but it's going to be even more influential in the next couple of decades. But anyway, we now have made available to people for the first time an audio book version of Humans 2.0. And so if people go to our website, reasons.org, and go to reasons.org/donate, they can, for donating any amount, they can actually get a copy, an exclusive copy, audio of the audiobook of Humans 2.0.
So that's now available print, as an ebook, and as an audiobook.
Yes, right. So 3 versions.
And hey, wouldn't it be fun to have all 3?
Yeah.
Okay, well, thanks, Buzz.
Yeah. Okay, Hugh, up to you.
All right, well, this picture I got here is basically talking about how astronomers are able to see really distant stars even without the James Webb Space Telescope. I mean, everybody's anticipating that once the James Webb Space Telescope starts doing real astronomical studies, one of the first things it's going to be targeting are the most distant stars. And the reason why is that until now, astronomers have not been able to actually image and study the very first stars that formed in the history of the universe. And which means you got to look back 13.6, 13.5 billion light years, because the farther away you look, the farther back in time you see. And this is a way that we can not only test the biblically predicted Big Bang creation model, but actually determine in more detail exactly what kind of Big Bang creation event occurred. So that's kind of the big mission of the James Webb Space Telescope, is to actually image and study the firstborn stars in the history of the universe and use that as a way to refine and further develop the Big Bang creation model. But there's a paper that got published a few weeks ago that says even before James Webb is up and running, there is a way we can image these very distant stars, and that's to use what's called gravitational lensing. And this image here basically shows you the technique where you got observers on planet Earth with their telescopes, and they look through an intervening cluster of galaxies. So that that little blue sphere that you see there, Basically, you got a distant cluster of galaxies. And what Einstein's theory of general relativity tells us is that when a beam of light passes nearby a massive body, it gets bent. And so, for example, we noticed in the 1919 solar eclipse, they could see that stars near the eclipsed sun changed position. And it was exactly what general relativity predicted. Now, the greater the mass, the greater the bending effect. And so if you got a dense cluster of galaxies, you get significant bending. And so what this image is showing is that you can use an intervening dense cluster of galaxies as a gravitational lens to see a galaxy far more distant than what's in between you and the cluster of galaxies. So it's a way to actually increase the magnification power of your ground-based telescopes. Now, there's 41, the Hubble Space Telescope's been used to survey the universe for suitable gravitational lenses, and they found 41 clusters of galaxies that do indeed serve as a gravitational lens. And I got a couple of images here basically showing you what it's like. And so we have an intervening cluster of galaxies here that gravitationally lens a distant galaxy. And the lensing effect is taking this single galaxy and makes it look like a ring around the lens. But as you look along the ring, you can actually study the individual features of that much more distant galaxy. Now, when you have a perfect alignment between the Earth, the densest part of the cluster of galaxies, and a much more distant galaxy, you'll get a lens of this quality where you get almost a perfect circle around the lens. That only happens if you got the perfect alignment. But more often you get something like this where you get a partial ring around the cluster of galaxies. So that little arc you see at the bottom there, that's a distant galaxy that has been lensed. But the one that people are really excited about is this one. And here you can see a long, very sharp circle around there. And as you look along that arc, in fact, I think it's called the arc galaxy because of how beautifully defined that arc is. And so you can look along that arc and you can actually see individual structures in the distant galaxy. Well, what has happened is a team of astronomers basically looked at this in much more detail with the most powerful telescopes, ground-based telescopes available, and they said, we've been able to image an individual star. Now, this isn't the first time they've used this technique to actually image individual stars in a galaxy, but up until now, the farthest they've been able to do that is out to about 10 billion light years. What is new is they've been able to find a gravitational lens where they're imaging a galaxy that is 13 billion light years away. Actually 12.9 to be precise.
So you would tell that from the redshift
Yes.
of the light, so that in that image you would actually, where you have the
little arc there.
The arc, you would see a discontinuity in terms of the redshift compared to stars that would be.
Well, this particular galaxy is a redshift of 6.2, which translates into a galaxy that's 12.9 billion light years away, which is only 900 million years after the cosmic creation event. So it's very close to the time when the first stars are forming. And so they were able to go in detail along that arc and to pick out a single star. And I think the next image actually shows you this star that they have found along the arc, that little thing over to the lower right. And they've actually named the star Earendel. So they're taking that out of, English ancient literature. So kind of following up with what you see in the Tolkien series of the rings. So they call it Earendel. And so what they've been able to discern is that this star, and in fact, they said, okay, we want to address the issue because a lot of people are going to think maybe you're imaging a star cluster rather than a single star. But they're able to do this in sufficient detail that they determined what they're imaging as less than 1 light year across.
Mm.
And star clusters are not that tiny. Now, they did say this might be a binary star, or it could be a single star.
Mm.
But we notice, and it's obviously a bright star, for them to be able to image it at that distance. And hey, what was impressive was the magnification power. Thanks to intervening cluster of galaxies, they were able to magnify this single star in this distant galaxy by a factor of somewhere between 1,400 and 8,400 times.
Wow.
So yeah, you're basically making your ground-based telescopes thousands of times more powerful thanks to this natural gravitational lens that's sitting there in the universe. So with that enormous amount of magnification, it indeed is possible that they could be imaging a single star if it's big enough. And they said even if it's a binary star, what we notice about binary star systems where you got bright stars, the brightest star dominates the picture. So it's like you can kind of forget about the second star that's orbiting the big star. But the bottom line is they were able to determine that the star that they have found is between 50 and 100 times the mass of our star, the sun, which is consistent with what we'd expect by what's called the Lambda CDM hot Big Bang creation model. Lambda standing for dark energy. It's the model of the Big Bang universe where dark energy is a dominant component and cold dark matter is a second most dominant component. You put the two together, it adds up to about 95% of all the stuff of the universe. And so they're saying, we know somewhere between 50 and 100. And they said, this is on the list. They've already got time scheduled on the James Webb Space Telescope to follow this up. And they said that'll give us actually a more precise measure not only of its mass, but of its spectra. And we're going to be able to use these gravitational lenses basically to guide the James Webb Space Telescope of where to look and what to study first in order to determine the physics of the firstborn stars. And fundamental to all Big Bang creation models is the universe starts off without any stars, and where in the first few minutes of the Big Bang, about 24% of all the hydrogen gets converted into helium. The universe begins with only one element in the periodic table, hydrogen. But as the universe cools from the Big Bang creation event, it spends a few minutes in the temperature range where nuclear fusion can occur. You get helium and you get a trace amount of lithium, but stars make everything else. But the firstborn stars, according to Big Bang cosmology, will be about 75% hydrogen, and the rest will be helium and a trace amount of lithium. And so the quest is, let's actually look for these firstborn stars and see if it fits what the Big Bang creation model predicts. And hey, we can measure it with a lot of precision. That'll actually help us to discern exactly what hot Big Bang creation model we're living in right now.
So the James Webb Telescope should be able to make those kinds of compositional measurements.
Yes. That was the main reason why they said, hey, taxpayer, give us $10 billion and we'll be able to put this telescope out there and we're going to be able to answer these really fundamental questions.
Yeah.
And there hasn't been a lot of talk about it, but the James Webb is going to be able to answer fundamental questions of creation, of cosmic creation. And this isn't the only thing it's going to be able to explore, but this is one of the first things on its schedule is to detect and measure these firstborn stars. But hey, thanks to these gravitational lenses, we got a head start, and it's actually going to help us make use of the James Webb Space Telescope more efficiently. So I'm looking forward to being able to write some blogs saying, hey, this is what James Webb has done for us. And keep in mind, the Bible said it first. The Bible, thousands of years before astronomers, had the observations to say, hey, we really do live in what looks like a Big Bang universe. You got 6 Old Testament Bible authors explicitly stating repeatedly, not just once, but repeatedly, that the universe has a beginning that includes the beginning of space and time itself. There are laws that in the universe are constant, they don't change. One of those laws is a pervasive law of decay, and you got 11 texts saying the universe expands from the cosmic creation event. So this is big deal. And by the way, I've got 2 blogs out there on, I think it goes back to our very first Facts for Faith magazine we published in 2000, where I teamed up with the theologian John Ray
Yeah,
to write the piece, Big Bang, the Bible
I
Said It
remember
First.
that.
And that article has been read by a lot of people, and a lot of skeptics have said, excuse me, oh, wait a minute. You're an astronomer living in the 21st century. You're seeing this by hindsight. Did anybody previous to the discovery of Big Bang cosmology in the 20th century see this in the Bible? So I got a follow-up article where I basically address that question and cite all the theologians, mainly Jewish theologians, who wrote about these cosmic features from what they knew in the Bible, literally 800, 900, 1,000 years before astronomers discovered Big Bang cosmology.
Yeah. Well, something that's fascinating to me about this discovery is the fact that the laws of nature are such that you wind up getting gravitational lensing, which makes these kind of observations possible. And so it's not only that do you see design in the universe that makes life possible, but the universe is discoverable. And it's a very interesting and technique to use gravitational lensing to be able to see behind
So you're
galaxies.
suggesting that maybe God wanted us to be able to read the book of nature?
Yeah,
Yeah.
yeah,
No, I agree with that. I mean, an analogy I've used is, we have the Bible. It's inspired by God, but God wants us to be able to read it. So he designed our eyes so we could read Scripture. He gave us the capacity to develop technology so we can get eyeglasses so that when we get older, we can still read it. Well, likewise, I kind of look at these gravitational lenses as the equivalent of eyeglasses that God gave us so we can actually read the entirety of the book of nature from the present all the way back to the very beginning.
yeah. So yeah,
Anyway,
so,
fun.
yeah, it is. So yeah, God not only designed the universe for life, but designed it to be intelligible and discoverable. So
Well, someday I've gotten why the universe is the way it is. He put us at just the right time in cosmic history and the right location in the universe so that we humans can actually read 100% of the history of the universe and discover his handiwork. Well, Fuzz, thank you for your comments about that. This has been a fun episode that I've really enjoyed what you were saying earlier. And hey, if you want to be able to access all of the social media outlets of Reasons to Believe, the key is RTB_official. That's your gateway. And if you're not already a subscriber to the Reasons to Believe YouTube channel, I encourage you to do that. And just don't look at the video clips we got, that there's thousands of them, but look for opportunities to share those with people. It's been my experience, Fuzz, that people watching our video clips on YouTube, a lot of them, that's how they come to faith in Christ. That's how they discover us. So I encourage you, share this with other people. And thank you for joining us at Stars, Cells, and God.